Hello, and welcome to another AerOx and Warwick Aerospace talk. Tonight we have the honor of being joined by Dr. Paolo Ferri, the former head of mission operations at the European Space Agency. Paolo studied theoretical physics at Pavia, from which he started his illustrious career at the European Space Operations Center in Darmstadt. He started in 1984 as an astrophysicist on the Exosat missions, followed by joining various operation teams in different missions from Eureka to the Solar Orbiter. From 2006 to 2012, he was the head of the Solar and Planetary Missions divisions, followed by becoming the head of mission operations, responsible for all ground segment operations and all robotic missions. Notably, he worked for 2 decades in planning the rendezvous and landing of the Rosetta Comet mission. We'll start by tonight with a presentation from his time at ESA, followed by an open Q&A, so please feel free to submit questions in the YouTube Live. Paolo, thank you for joining us.
Thank you. Welcome all. I start sharing my screen now. I hope should be okay. Can you see the presentation? Okay, very good. So, right, title is Half a Century of ESA Mission Operations. I haven't worked that long, although I worked actually 36 years in operations. And I joined the European Space Operations Center, what we call ESOC, in Darmstadt in Germany, when it was 17 years old, and now it's over 50. So I can say that I saw it growing. You know? But let me start saying a few words about the European Space Agency for those of you who are not fully familiar with it. It's an intergovernmental agency. It has nothing to do with the European Union, and but the majority of the states that compose it are actually EU states. There are 3 exceptions, Norway, Switzerland, and recently the UK, because the UK left the European Union, but not ESA. In fact, it's a very strong partner. We have also other cooperation agreements with other states that then gradually join us. In total, we have 22 member states. The sites and locations of our centers are spread around Europe, but also we have, of course, ground stations, which is a big antenna to track our satellites, and offices in the world. Of course, the center of the universe is the control center here, ESOC in Darmstadt. All the rest, there's the administration center in Paris. There is a big technological center in Noordwijk in Holland. A relatively smaller center in the UK, and so on. But as I said, since I spent all of my career in this place, what we will talk about is really what that place does for the European Space Agency missions. And what that place does, ESOC, is basically can be divided in 2 big areas. On one side is the mission operations, which is actually my field. So these are the people that actually press the buttons and fly the missions, which doesn't mean only pressing the button. Of course, there's a lot of preparatory work. We develop mission concepts. We specify the requirements for all the ground facilities that then get either built or at least customized for the different missions. We simulate the various mission scenarios. We train our operator teams, and then we execute the mission. The other part of ESOC is the ground segment engineering. And these are people that, of course, together with European industry, develop the tools which we need on ground to operate the space segment, which is the satellites or the probes. Practically, antenna, communication systems, computers, simulators, and an important part of this department, which is a bit bridging between the 2 departments, operations and engineering, is the flight dynamics group. They develop their own tools, but also they are operating all the aspects of orbit control and attitude control of the satellites. This was the start. Actually, in 1966, ESOC did not exist, but there was a computer center in ESOC. And this is a picture from a newspaper from those times, where I highlight here that this computer all what you see in this room was capable of 300,000 basic operations per second. So it was quite impressive for those times. I guess by now your mobile phone has overtaken this by several orders of magnitude. In 1967, the center was converted into an operations center. And in fact, the first operation we flew was, the first satellite we flew was this little satellite here called ESRO-2 in 1968. I think it was launched in May. Again, this is all before my time, but this was a sort of historical first for Europe, the first European satellite. In fact, at that time, ESA was not yet called ESA. There were two organizations. One was called ESRO, I guess was European Space Research Organization, and ELDO, which was the equivalent for launchers. They were developing European launchers. They eventually joined the two organizations in 1975. But okay, of course, we consider ESRO the precursor of ESA. The mission control room at that time looked like this. Practically, there was very little information coming in real time from the spacecraft. A few light bulbs that would go on and off, a couple of numbers and plots on a strip chart, telephones, of course, with the ground stations. The telemetry of the satellite, the majority, for example, the science telemetry, at that time would be collected via tapes directly, physically from the ground stations. I know of colleagues who went, they traveled to the Falkland Islands, for example, to just collect the science telemetry. There were no communication lines between the ground stations, which would receive the telemetry from the satellite, and the control center. And you would transfer the big amounts of data, you would transfer them by tapes, by magnetic tapes. I jumped to 1975 because this is when the main control room was upgraded. And you see already it looks a bit closer to what it looks today, although with all this wood now it doesn't sound very modern, but it's more or less what it is today. And you see at that time we have this table, which is an historical table where we actually glue letter by letter the names of the missions on this table here. You see already in 1975 we have launched all these satellites. And these are the launch dates. Now, you will see it later. Nowadays, we put also the launcher. At that time, we were using American launchers for our satellites. We didn't have yet a European launcher that only came in the 80s. The initial, say, specialization of our satellites was mainly, okay, first I want to say that we were gradually developing also a ground station network. This is one example, the Villafranca station in Spain. Typically a network of antennae which had a 15-meter diameter. And they were pretty good, and we still have antennae of this size to operate satellites which are in orbit around the Earth. They are pretty good for that. If you leave the Earth, you need something bigger in order to collect the very weak signal that comes from very high distances in deep space. We were specialized at that time in what is called the geostationary orbit. I think all of you have already heard about that. Basically, you can put on an equatorial orbit a satellite to a radius. In fact, it's this radius here compared to the center of the Earth is 42,000 kilometers. It's about 36,000 kilometers altitude. Of the circular orbit, so that it actually rotates with the same speed as the rotation of the Earth. And therefore you can use it very nicely because from the Earth, you see it basically fixed in the sky. Typically used for telecommunications in the beginning. Now it's used for broadcasting, also for meteorological satellites. It's a very busy orbit up there. In order to get there with the launchers, normally you get parked on a low orbit, a few hundreds kilometers, either an orbit like this, which is just a circular orbit, relatively low, or an orbit which has a pericenter where the launcher has deposited you, but it has a bit more energy. so it can have an apocenter close to the geostationary orbit. So to get on the geostationary orbit, which is this circular one, you need a process which is called, or a technique which is called Oman transfer. Basically, if you are on the low orbit, you fire a engine here so that you increase your energy, you increase your apocenter, and then when you're here, you fire it again and you circularize the orbit. So that's the technique that we were specialized in the 70s. Now I jump to 1983, where we launched Exosat. Exosat was a very important milestone for the European Space Agency for various reasons. First of all, it was the first satellite. You see it on this side already, compared to the one you saw it in an earlier slide. This is already a 500 kilo satellite, so quite heavy for those times. Again, launched with an American launcher. But it was the first European satellite with a reprogrammable onboard computer. Up to then, up to the 80s, everything was hardwired on board the spacecraft. Any logic, any circuitry was hardwired. This one had a reprogrammable computer for just for the payload, in order to compress the data, because the downlink was still relatively weak, 2 kilobits per second, I think. Well, 2 kilobits was the uplink. I think it was a few kilobits per second, the downlink. The data that it was collecting, this was an astronomy satellite in the X-ray band, had to be compressed. So you had to do really data crunching on board before downlinking it. And this computer was there for the scientific data. But we happened to use it in operations also to overcome failures that maybe I can give you a couple of examples. The second important milestone of this satellite was that this was the first satellite of my career. So very, very important for this talk, of course. The satellite was launched on a highly elliptical orbit. The reason was that for astronomy satellites, if you're on an elliptical orbit like this, the period was 4 days. You spend, for the second law of Kepler, you spend most of the time in this area. Your satellite is very slow when you fly away from the Earth. Of course, it goes very fast across the pericenter, the perigee. So practically, your telescope is not disturbed by the Earth for most of the orbit. When you come down here, first of all, you get the Earth in the field of view, so you're disturbed. Also, you go below the radiation belts, which surround the Earth at a certain altitude. So your instrument, especially for high energy astrophysics, you have high tensions, high voltages. So you have to switch them off. So we had to periodically, over 4 days, we had to switch off the payload for a few hours. Maybe in the worst case was half a day. Sometimes it was even shorter. But most of the time we were free to observe. That's where we put all our telescope in the past. Now we put them somewhere else. I will explain you later. A picture, not very nice picture, of the control room at that time. You see, individual parameters of the telemetry were displayed on these handmade, custom-made, bespoke big panels for that mission. Of course, nowadays it's unthinkable. First of all, because we can reproduce anything on big screens with a computer, but also because we have tens of thousands of parameters. Here we were talking about a few hundred parameters of telemetry. So we could show the most important ones up to these screens. The other screens that we had in front of us, the spacecraft controllers, were using just alphanumeric screens you see up here. But we had, they were just alphanumeric and black and white. We had more sophisticated computer screens, again, for the payload. I belong to the payload group because I joined as astrophysicist, although I was working in operations 24 hours cycle. So we could use these computers, which were more sophisticated. And in fact, like for the onboard computer, we developed programs on these computers that actually were helping the actual spacecraft controllers to do their job. So we were a bit of the edge between the hardwired world and the computerized world of today. The big jump there was with Giotto. Giotto was the first mission, together with a fleet of other satellites, that actually went to encounter Comet Halley. Comet Halley is the most famous comet, which comes back every 76 years to Earth. And the first time it came back to Earth during the space age was 1986. So in 1985, the European Space Agency, the Japanese, and the Russians put together a fleet of probes to go and do not a rendezvous, but a flyby of the comet. The control room was refurbished completely. We had more sophisticated color displays there. But really, what was important of this mission for the growth of our center was this was an interplanetary mission. We were not going too far from Earth and the Sun. You see, we stay on a very similar orbit as the orbit that the Earth has around the Sun, to encounter Halley. In fact, Halley was traveling against the rotation of the planets, of our planet, and therefore also of our probe. So the relative encounter speed was enormous, was 68 kilometers per second. This can happen when you go to visit comets. So the encounter was very, very short. And of course, it was dramatic because we wanted to get as close as possible to the nucleus. So we targeted about 500 kilometers from the nucleus. Eventually, we flew about 600. But we crossed the dust cloud that surrounds the comet, and this was quite dramatic for our spacecraft. Here you see we had to build an antenna in Carnarvon, which is in Western Australia, because the encounter took place when the comet was actually better visible from the southern hemisphere. We didn't have antenna in the southern hemisphere at that time. We built one. But because the distance to the Earth was not so big, we could still afford a 15-meter antenna at that time. This is putting together the last pictures closer to the encounter. It's not a very quality video, but you see here the distance in kilometers. And you see the camera was programmed to follow a very bright object because everybody thought the comet nucleus would be like a snowball, a piece of ice, so extremely bright. But as you can see in the pictures here, what eventually we ended up pointing at was the dust and gas jets on the surface. The nucleus itself is extremely dark. This is true for all comets, but at that time, nobody had a clue of what a comet nucleus would look like. So we were all focused on tracking a very bright object. And of course, this was happening at about 10 minutes propagation delay. It means that our signals were taking 10 minutes to get to the comet, to get to the probe. So there was no way to steer it. Everything had to be pre-programmed. Fortunately, at least while we were tracking these gas jets, but still in our pictures, the nucleus could be very well imaged, maybe from from a relatively larger distance. Yeah. So this was a big success. Eventually, the probe survived, and we managed to do other comet encounters in the future. But the camera was killed by the encounter. Basically, the relative speed was so high that the very fine dust particles that surround the comet, I'm talking about dust particles that look like smoke particles, really microscopic, but they work like sand, and they destroyed anything that was picking out of the protection screen that was mounted on this side of the probe. And in fact, the probe lost about 2 kilos of material, just removed by the drag of the sand, of the dust. Here I come to my first love, which is the Eureka project. Here I was still very young at that time, in the 90s, and I spent a lot of effort. The spacecraft was, first of all, a very exciting mission because we flew with the space shuttle. So it was brought in orbit by the space shuttle, released there. Then we would maneuver it to a higher orbit, stay there for a few months. Planned was 6 months, eventually became 11 months, and then come back, rendezvous with the shuttle. A second shuttle would bring us back to Earth. It was a retrievable carrier to perform microgravity experiments. So we wanted to bring back the samples. It was a big spacecraft, 4 tons. And again, working with NASA and working with the shuttle environment and the manned space flight was a fantastic experience for a young guy like me. But also the spacecraft was, from the design point of view, was extremely modern, in fact, futuristic, I could say. But from the construction point of view, it was still a spacecraft of the 90s. And in the 90s, like in the 80s, spacecraft would fail continuously. Yeah, they would be designed for 2 years in orbit, and after 1 year, like Exosat, they would lose all the redundancy. Payload would fail. Eureka stayed 11 months in orbit, and we lost 2 gyroscopes out of 6, half of the solar array panel, so power from the solar array. We lost 3 payloads. I mean, this was hardware failing all the time. And this was still the spacecraft that we built, the European industry built in the 80s and beginning of the 90s. If you look at what happens now, we are still flying satellites that were built at the end of the 90s. Obviously, the European industry needed this learning curve. It was a very fast learning curve. But since this millennium has started, hardware failures in flight, of course, still occur, but they are much more of a rare occasion. Today, we struggle with software. Anyway, let me show you, first of all, the control room of Eureka, again, with more modern displays, but we were still confined to a single page with alphanumeric displays per screen. So, in fact, this was a workstation with 3 screens. All we could do was to display 3 windows today, we would call. Now, our operators on a display can display 20 windows and click between one and the other. At that time, we were constrained to this limitation. Of course, you could page them through, but it was a pretty tough limitation. You had to work very, very concentrated and disciplined on the few information you could display at the same time. By the way, if you look at this guy, it's actually me in 1992. So this is a demonstration that I used to have hair and even dark. Now, let me show you this video. I will keep the
cargo bay doors were open.
The volume down. This is what, after launch on the 31st of July, in fact, the day after launch, on the 1st of August, the shuttle was supposed to do. An astronaut would operate the remote manipulator system, the RMS, pull out Eureka, do some turns to test some of our optical sensors to make sure that we were actually, all of these things were working before releasing the satellite. Then keep us there, let us deploy the solar arrays. I'm going a bit faster because otherwise this would last too long, and then release us. And then at that point, the shuttle would move away, and then we would actuate our onboard thrusters and go away from the shuttle. You see here the images on the 1st of August where our astronaut, was a European astronaut, Claude Nicollier, grappled the Eureka with the remote manipulator system here. Eureka is there, and here is lifted.
Very gently out of the cargo bay.
Now, I will never forget this image because in this moment we started having enormous problems with the telemetry from Eureka. We didn't know what was going on. Telemetry was coming through the shuttle. There's a small antenna on the shuttle cargo bay, which is called the PI link, Payload Interrogator link, where the astronauts and we can actually send commands through the shuttle link to the Earth and receive telemetry through that. Due to an incompatibility of the two systems that was not discovered during testing, we were losing telemetry all the time. And NASA was also quite nervous because some of this telemetry had to be monitored by the astronauts. It had to do with their safety. We had 600 kilo of hydrazine on board, and they wanted to make sure that it would not freeze. You hear here on the voice loop all these problems with telemetry. You hear problems, you hear failures.
Telemetry at this time? No, we have not been able to lock up good on you since you went to your dead end side.
Okay. Mass has just reported their antenna as being red.
So while we were struggling with this problem, we tried to use our antenna from ground. And you hear my voice. So one of our antenna was not working at the right moment. So everything was delayed in this day until eventually our batteries was running basically out of energy. And we decided to deploy the solar arrays commanding from the ground.
Was the deployment of the
this was not planned to command from the ground. It was not planned to do it in sunlight. It was forbidden by the flight rules, but we had no choice. This was our last chance to manage to deploy the antenna. We could not rely anymore on the link via the shuttle. And you can see here gradually the panels of the solar arrays opening. This was a big relief, because as soon as these things opened, we knew that we had more time to scratch our head and think on how to continue. Here I'm going a bit faster. You see the solar arrays deploying there. After the deployment, we decided to park the spacecraft overnight, and then the next day we developed a new procedure where we would use only ground antenna. We still didn't understand the problem of the communications via the shuttle. We understood it only a few days later. And if you're interested, I can tell you what it was. It was really a stupid thing. But I don't want to bother you now. What is interesting here is to see also some images, which is Eureka flying over the Cape. What you see down here is the starting point of the mission where the shuttle was launched. We had problems also when Eureka was flying alone, completely different problems. Here you see the spacecraft seen from the shuttle and the moon in the background. But eventually we made it. We made it. The shuttle could continue its own mission, and we could continue with our mission. And we went on for 11 months. Here you see a picture of Eureka parked overnight. So we delayed the shuttle mission by almost 1 day. And here you see a better quality picture of Eureka flying over the Earth. The mission went on with all the problems that I mentioned before: gyroscopes failing, payload failing, solar arrays failing. But we managed to run the mission to the end. And in 1993, in June, we were back for the retrieval. Another shuttle came, and we met in space. You see the spacecraft all yellow now. This used to be white. This is from the flight up there for 11 months. There is atomic oxygen, all sorts of rubbish that actually eventually corrupts your surfaces. Also micrometeorites, by the way. It was grappled by the shuttle, and at this stage the idea was, okay, we close the solar arrays, we close the antenna, power flows through the RMS, the remote manipulator system, and we can put back the spacecraft into the cargo bay. Now, what happened was that our antennae, which were located one on this side, one on the other side, did retract, but they didn't latch. And this was a flight rule. The shuttle was not allowed to come back to Earth if our antennae were not latched. So we knew why. It was simply that the MLI, the multi-layer isolator here, the cover of the spacecraft, had been deformed a bit, and the antenna, the latch, the little hook that would latch the antenna, could not move properly. So what we said was, okay, we get an astronaut out, you see, mounted on the RMS. We had to bring the spacecraft back into the cargo bay, and then we got an astronaut out. And while we were bringing preparing the spacecraft to send the latch command, The astronaut was out. David Lowe was his name. At the right point, I was there in the console in ESOC, and I would say, okay, now the astronaut should push. And he had to push with his finger the antenna against the MLI, and then at that moment I would send the command to latch the antenna. And it did work. It did work, but it was a super complex and super dramatic procedure. So Eureka kept us extremely busy for all this time until the very last moment, but it was a very exciting mission. So another mission that I moved on after Eureka was cluster. And I'm not going to talk very much about cluster. Again, we did an upgrade of the main control room. You see, it's the same room that you see with the wood there, you saw in the picture of 1975, but we enlarged it on the side, because cluster was a fleet of 4 satellites launched together. We wanted to have at least 2 workstations dedicated to each satellite in front. So we had 8 workstations here. And then we had the position of the operations manager, which was me, and another guy who would supervise the operations of all 4. So this was a complete refurbishment of our control room. But 37 seconds after launch, we flew on Ariane 5, and this was the first test flight of Ariane 5. It was supposed to be free, and we found it was a very, very convenient offer, but sometimes you regret that because of another stupid software problem, which again, I'm very happy to explain to you if you want later. Ariane 5 exploded after 37 seconds in front of our eyes, in an altitude of about 4 kilometers. Spacecraft were destroyed. These are all the pieces coming down. They fell so there was the explosion, the fire. They fell from 4 kilometers. They fell into salty water, into the mangrove swamp in front of the coast of Kourou in South America. Nevertheless, we retrieved, our colleagues retrieved some of the electronic units, and they still worked, which shows that really European industry was getting better at building satellites. The good news about cluster is that it was rebuilt, thanks to the fact that industry was ready to build, like in a chain, build 4 satellites. We managed to put together one within a few months from the spare parts, 1 full satellite. And then for a relatively small amount of money, still 200 million or something like this, but it was a quarter of what the original mission cost. They built other 3, and they're still flying today. And they're flying with batteries which are so old that they don't work anymore. So the satellites work without battery. They go into the shadow, they die. When they come out of the shadow of the Earth, they start again the computer. Sometimes we have a lot of problems with them, but then we sort them out. It's amazing. And the mission is flying since the year 2000. And 2 also very, very old missions, still on high elliptical orbits, are these 2 telescopes, XMM, Newton, and Integral, one in X-ray, the successor of Exosat, and one in gamma ray, so both high-energy astrophysics telescopes. They were launched around the turn of the millennium, and they still work. They are still extremely healthy, and they are relatively old in terms of also conception. For example, they are controlled in real time. There's hardly any memory on board to store commands, to store telemetry. So they are constantly in contact, apart from the small pericenter passes. And yeah, you have to have people, and in particular computers, talking to them all the time. While all the more modern satellites now, you actually load commands offline, you prepare them offline, you load them during a pass, and then they execute for a couple of days in the future. And you download the telemetry during the contact, the telemetry that was collected during the non-contact period. So for most of our satellites today, we don't need to be in contact all the time. Maybe, I mean, there's been cases with Rosetta during the cruise, we were in contact for once per week. And this happens, some of the Earth observation satellites, they have a contact once per day, but they have other contacts with other automated antennae just to download their data. Another thing that happened, I didn't participate to this, but this was a milestone for ESOC, was the landing on Titan. In fact, we flew as a passenger of Cassini. Cassini was a fantastic Saturn mission of NASA, finished only a few years ago. But in 2005, at arrival at the Saturn system, it delivered our probe, which was a landing atmospheric probe, to the surface of Titan, which is one of the biggest moons with Saturn. And the probe was so successful, it was only working on batteries, so it was supposed to survive only a couple of hours, 2.5 hours, I think. But it was so successful that actually it survived the landing, and it delivered unexpectedly also pictures of the surface of Titan. And today, this is still the further object that we have landed on in the history of space flight. Of course, the control room at that time was full of people also because there was nothing to do. Everything was pre-programmed 5 days before. We were just monitoring. Yeah? So there were ministers and big bosses around, and the operations manager at that time just sitting there and looking busy. This I want to tell the story because in 2006, in August, I became responsible for all interplanetary missions. So actually, I missed the Cassini-Huygens just for a year. But at this stage, I was already working on Rosetta since 10 years. So Rosetta was still under my responsibility as flight director. But then I got the responsibility for Mars Express, for Venus Express, and other fantastic interplanetary missions. And one of them, which is not interplanetary, but it belonged to this division, was Smart 1. Smart 1 was a technology mission to the moon. The idea was to test a ion engine, so solar electric propulsion. But of course, it carried scientific payloads, and it worked pretty well for 3 years around the moon until September 2006, until it was spiraling down because we ran out of fuel, and it was about to crash on the moon. And our flight dynamics people, who are really fantastic guys, predicted that it would crash on this hill, which is about 100-meter high on the moon, which is actually this one here. You see there. You can see the cursor, right? These are the orbits that the spacecraft was flying at that time. They would last about 6 hours. And they predicted that over this orbit, it would hit, it would hit this hill. This was a Sunday morning, 7 o'clock in September 2006. We invited all the VIPs and politicians and directors. And on Friday night, remember, I just became responsible of this mission from a managerial point of view 1 month before. They called me and they say, actually, we were called by an American scientist. He claims that we will crash against this crater and not against this hill. And this would be 6 hours earlier. You have to understand that at that time, the orography of the moon was still known pretty roughly, in squares of one kilometer, the altitude of the place. So we didn't have a very accurate map of the moon. So we said, what do we do here? And our flight dynamics people had a brilliant idea. We had run out of fuel, but we still have some cold gas that we use to offload the momentum of the reaction wheels, which are needed for attitude control. So they oriented the spacecraft over that weekend in the right direction. They used all this cold gas pushing to the end, and they managed to increase this altitude by 200 meters. And this was enough over that night between Saturday and Sunday to fly over this crater, and in fact, 6 hours later to crash into this hill. It was a big relief, but it was my first and last encounter with this mission. I will never forget it. In the meantime, we had prepared for the big jump into interplanetary flight. Up to then, all we had, up to the beginning of the year 2000, we had flown only Giotto. We had some people who had worked with NASA in Pasadena to operate our Ulysses mission, but really we didn't have any interplanetary experience. We had to build it up from scratch, starting for the mission of Rosetta, which was supposed to start in 2003. And not only the experience, but also the infrastructure. So we built, first of all, a deep space antenna in the southern hemisphere, Western Australia, New Norcia. It's just north of Perth. And this is a 35-meter antenna. You can see here how the beam goes into the antenna. This is like a reflecting telescope. You can see here what this thing weighs, and you see it's a total weight of 600 tons. And this thing has to be oriented and kept pointing within a fraction of a degree. So it's really a masterpiece in many areas, not only communications, but also mechanics. We first used it for Mars Express, although it was built for Rosetta, but Rosetta was delayed in 2003 by another problem of Ariane 5. And so Mars Express was launched in June 2003, and it was the first mission to use this first deep space antenna. Mars Express, again, another incredibly successful mission, arrived Christmas 2003 at Mars. And it's still flying today, and it's still very successful, and it's still pretty healthy. It lost a couple of thermistors, a couple of channels in in one or two instruments. So really an extremely successful mission. One problem that happened with the Mars Express was that we carried this time a passenger, like Cassini had carried us, Huygens, to Titan. We carried a passenger, which was a British lander module. Beagle 2 was called, and we released it nicely at arrival at Mars. Since then, we never heard from it, and only very recently it was spotted by an American satellite, and which showed actually that the landing did work to a large extent. The spacecraft, the lander was not destroyed. It only had failed to fully open, and therefore it could not communicate. We learned a lot from this mission. We learned that if you do a landing, you can afford to fail it, but you cannot afford not to get any information about it. So we failed twice with Beagle. The landing failed. It was not our fault, but we failed in not designing the mission such that it would keep communications during these minutes of landing. This is vital because you can afford to fail in deep space, but you want to learn from that. You'll see what we did with this experience here. Okay, this shows another Oman transfer, but not to increase the altitude of the orbit of the Earth, simply to increase the altitude of the orbit around the Sun. So we launched from Earth orbit, we pushed it into a transfer orbit, and then at arrival at Mars, we had to do another maneuver in order to get injected into the Mars orbit and then in orbit around Mars. And this is another example of these fantastic pictures that Mars Express is delivering to us. In the same decade, ESA decided to build a cheap mission and very fast mission. It was approved in 2003 and launched in 2005, using basically a carbon copy of Mars Express, doing just small deviations and going to Venus. And this was the first mission for which I was flight director in the control room. It was really exciting. We launched in November 2005. We arrived in April 2006. And the mission again was planned for 2 years, but it continued working for almost 10 years. I think it finished end of 2014. Very successful Venus mission. Then let me spend some time on Rosetta. This was my pet project. Yeah, 20 years I work on it, as was said in the introduction. The launch was supposed to be 2003. I started working in 96 in the preparation. We had to invent everything from scratch. Of course, all what we could copy, we did from our colleagues in NASA. We visited JPL. We asked them here and there, what do you do? How do you do this? And so on. Our flight dynamics people were also helped a lot in the beginning by NASA. But then during this mission, we became totally self-standing. And from launch onwards, we became adult. at the end, when we arrived around the comet, we could operate the spacecraft and navigate the spacecraft around the comet, and NASA was not able to follow that. So they are learning from us now. It's another wonderful example of cooperation where they helped us a lot to grow, and now we are giving back with our unique experience. So 10 years travel, 4 gravity assist, astral flyby, distances 800 million kilometers from the sun. This was an absolute record at that time with solar arrays, because our satellite, our probe, had solar arrays, 1 billion kilometers from Earth. And the plan was to rendezvous with a comet in August 2014, land very shortly after. We wanted to land when the comet was still relatively quiet, and this was at a large distance from the sun, 3 astronomical units, 450 million kilometers, for an end of mission in 2015 originally. This shows why it took so long. We didn't have enough energy to reach we wanted to do a rendezvous, so reach the comet with the rocket. So we had to use gravity assist from Earth. You see, the first one was just 1 year later. Then we used Mars to actually simply bend our trajectory back to Earth, where we encountered Earth for the second time here. We got the second kick. And at this stage, we had a much higher energy, but still not enough to reach the orbit of the comet. You see the comet going through here. Again, when you fly when you want to do a rendezvous, distance is not the problem. The problem is speed. With the third gravitational assist, we were actually faster than the comet. So, okay, we crossed twice the asteroid belt. We did flybys of asteroids. And then we came to distances where even our solar array, large solar array, was not sufficient to supply power to the spacecraft. We had to hibernate it for 2.5 years. When we exited in January 2014, we were almost there, 9 million kilometers still to go. After 7 billion, this was just around the corner. And then our mission would really start. Eventually, we flew around the comet for 2 years, almost 2 years. This is the principle of a swing by, for those of you who are not familiar with it. Again, forgive me about the quality of this because I drew it myself. This is your trajectory close to the planet. You go in with a velocity vector, the planet accelerates you, but then it slows you down when you go away. So eventually the result in the frame of reference of the planet is that you simply bent the velocity vector, but you have not gained any energy. This thing has not done any work. So why do we do that? It's because the planet is actually flying around the sun. So it has also angular momentum, it has orbital energy. And if you do now, with respect to the sun, you do a simply vector algebra, your incoming velocity was this, and your outcoming velocity was this. So in fact, you have gained energy. And this energy you've actually stolen to the Earth. So if you have the impression that the years are getting longer, it's also our fault. We did it 3 times. Yeah? So we have actually slowed down the Earth around the sun. Small deviation now away from Rosetta, because in 2009, while Rosetta was flying, we launched these 2 wonderful telescopes, one in infrared, one in microwave, Herschel and Planck, to a Lagrange libration point. Again, I don't know if you're familiar with the Lagrange points, but you can imagine they are sort of equilibrium points in the dynamic system Sun-Earth. Some of these are pretty intuitive. Imagine L1, imagine the gravitation force of the Earth pulls on this side, the one of the Sun pulls on the other side. In the middle, there is a certain point where they are in equilibrium. The other ones are less intuitive. They've got to do with the fact that it's actually a rotational system. So there are inertial forces also involved. So even here, by the way. So in fact, here you have the centrifugal force that counteracts the gravity of these 2 bodies. And here it's even more complex to explain. But again, if you're interested, we can go into it. But bottom line is, you can actually put a spacecraft around this point or around this point, and this you have an ideal observatory point here for the sun, or you have an ideal universe observation point here, because here you can point point the celestial sphere on this side, you have the Earth on your back, the Sun on your back, and actually you rotate around the Sun synchronous to the Earth. So you can always observe the stars and not being disturbed from the back by the Sun and the Earth. So today we put our telescopes not anymore in elliptical orbits, but we put them in this wonderful place thanks to fantastic mathematicians like Lagrange. Okay, here is another drawing where you see let's say the field, and you see that these are actually unstable equilibrium points, but they are equilibrium points. And I emphasize L1 because I show you here what we did with LISA Pathfinder. In fact, the initial part, increasing the altitude, was due to the fact that we used simply a two-week launcher for cost reasons. But eventually, once we got to the right energy to escape from Earth, by the way, this was a very tough operation. We escaped Earth. We went around this ideal point. It's about 1.5 million kilometers from Earth. It's not very far. And we entered this very large orbit, so that then you can always have communications with the spacecraft. You're not disturbed by the Sun, who is basically looking through this hole. So that's what we did with LISA Pathfinder. In fact, it's not an observatory. LISA Pathfinder was a test mission to verify the possibility to detect gravitational waves in space. And the reason why we sent it there was, again, it was one of the least disturbed points we could reach from a gravitational point of view. In the meantime, our network grew. After New Norcia, which you saw before, we built 2 new antennae first in Cebreros in Spain, 2005, and then in Malargüe in Argentina, 2012. I think this is Malargüe. They are almost identical. New Norcia works in the Sierra and X-band, while these two work on higher frequencies, X-band and Ka band. And now I go back to Rosetta, because in doing the asteroid flyby, we tested a new technique that was new for us. It was also used by NASA before, which is called optical navigation. This is the flyby of Lutetia. We flew by this big asteroid. It's 132 kilometers wide here, at a distance of about 3,000 kilometers, 3,500. What we did was what we call now optical navigation. You see, we took pictures of the asteroid, which, trust me, is this little dot in the center of the flashing circle. By taking successive pictures and pointing where you think the asteroid is, you see the stars in the background move. So you can improve dramatically the knowledge of the position of the asteroid with respect to your direction of flight. Why we needed this? Because with our radiometric data, we could determine pretty well where the spacecraft was. But we had to fly by an asteroid, and the asteroid doesn't have a transponder, a radio transponder on board. So at that time, the position of this asteroid was known within, say, 100, 200 kilometers. So we wanted to be sure that the relative flyby was pretty accurate. So this was the error with our radiometric measurements. This is called the B-plane. I'm reluctant now to explain what it is. Again, if you're interested, ask me afterwards. But anyway, this is where we were targeting. And when we did the first, we were targeting here. And when we did the first images, we saw that we are actually here. So we did maneuvers, just a few centimeters per second, to move our target into here. And then we did it successively. So if you enlarge this one, we did more and more pictures and better accuracy. And I don't think we maneuvered anymore. We found out that we were pretty good. Eventually we flew by here. Our target was the green one, in fact. And so this was good enough, just a couple of tens of kilometers. When we finally arrived at the comet in 2014, these are the pictures that we took the last days before arrival on the 6th of August 2014. These are pictures of this incredible object, rotating with a period of 12 hours. Yeah, don't be frightened. Yeah, this is accelerated. We stopped at a distance of 100 kilometers. So we were flying, of course, in formation. We didn't stop around the sun, but we kept a distance of 100 kilometers because we didn't even know the mass of this object. It was totally unknown to us. So we did these strange arcs, and then we measured how these arcs were bent by the extremely weak gravity of the comet. By doing that, then we did another 3 arcs at 50 kilometers distance. By doing that, we had a pretty good estimation of the mass of the comet, which was about 10 to the 13 kilos. It was 10 billion tons, 10 billion tons. And finally, we could try to get closer at 30 kilometers and do sort of half Keplerian orbits. You see, we were getting very, very cautious around it. We bent our inclination. Forget about this if you're around the planet. Yeah, you can only do it because this gravity potential is extremely weak. Then we went down to 20 kilometers orbit, then 20 times 10, and then 10. And finally, we knew enough about the nucleus to navigate accurately enough and to deliver the lander. This was the most difficult part of the mission. This was real pioneering. Nobody had ever flown around a comet in a very dynamic environment, totally unknown. No mission ever tried to land there on an object without having had a precursor mission that would characterize it for it. So we had to do all on our own and very quickly because we wanted to land in November. Just to give you an idea, this was the order of magnitude. So this is kilometers per second square of the forces that were acting on Rosetta. This was the gravitational force. This was the radiation pressure of the sun. So when we were at distances of 100 kilometers, they were the same order of magnitude, the gravity. Of course, then we got closer and we increased by 2 orders of magnitude, but still 10 to the minus 8 kilometers per second square. This is really extremely faint. And this was not the only thing we had to model. We had to model other things like, for example, the drag, which is this orange thing, the drag which was caused by the gas and the dust, which were still around the comet, even if it was not very active. And we had to model the higher potentials of the gravitational field because the comet was not a nice ball or a nice sphere like a planet. This was an extremely complex object. And even the shape caused, you see, these are the second harmonics of the gravitational potential. And they were causing forces which were comparable to the radiation pressure. So this was an extremely difficult task. And this was all to be modeled while we were there. So it was like flying, learning how to fly while you're flying. And we had to navigate, to use optical navigation to determine the relative position and distance in a different way. Now the comet was not like the asteroid, a point source. It was an extended object. So we had to take reference points, landmarks. We collected about 150, put them in a database, do a digital model, and do triangulation between successive pictures in order to see where we were flying, where Rosetta was flying with respect to this thing. Extremely complex. And in the early weeks around the comet, I used to go down in the evening before going home to the flight dynamics room, and there were always 20, 30 people there around the clock comparing pictures and trying to keep this probe in the right orbit. This was really heroic of these guys. Eventually, we developed even autonomous recognition software for some of the landmarks. So eventually the job became a bit easier. These are the milestones of the landing. I'm not going to go through that because I'm taking otherwise too much time. But basically, we flew on an orbit of 30 kilometers from the surface. And then we did a dive here, a maneuver to go towards the comet, released the lander like throwing a stone from a distance of 22.5 kilometers, and then maneuvered away Rosetta so that it could observe and collect the radio signal from the lander. These were the moments of the landing. We were all super happy until we found out that the thing had not anchored itself to the surface. So we spent 2 hours really totally scared of losing the signal. We were lucky; the signal was never interrupted, and eventually it stopped. We knew it would stop somewhere, but we were really scared that we would not be able to reacquire the signal if we lost it. We kept it, and Philae eventually could run its mission for at least 3 days, which was the basic mission. The engineers who built this lander built a machine for the unknown, so they didn't really know what we would find on the surface, and that's why they decided to put a big battery in it, so that at least all the instruments could be operated at least once, and that's what Philae did. Then when the battery ran out 64 hours later, as planned, it was in a dark area, so we couldn't use the solar cells on the surface, which anyway were very weak. They would deliver only 6 watts in the best case. So it would have taken, let's say, maybe a couple of weeks to do more operations, but we couldn't continue the mission there. So we continued the mission of the mother spacecraft, of course, which had 12 instruments on board and was supposed to characterize this comet. And we stayed around the comet for 2 years, as I said. And in some moments, in fact, in August 2015, the comet got very close to the sun. Well, not very close, still further than the Earth, 1.3 astronomical units, but close enough to be so active. You see here, these are pictures taken every 3 hours. You see even explosive activity, like a geyser explosion here on the surface. It was very difficult to stay close to it, mainly because the density of the dust around the comet got so high that our star trackers, which are sort of little cameras, telescopes that observe the sky, recognize the constellations, and keep the attitude, could not see the stars anymore. Instead of seeing the stars, they were seeing this sort of snowstorm. These are real pictures from the star trackers. It shows what the dust was doing to us. Yeah. So, as planned, we had to go away. This is a plot across the 2 years of the distance between Rosetta and the comet. You see, this was the approach in 2014. Got closer and closer. You see the 100 kilometers, then the 50, and then closer. This was the delivery of the lander. Then we started going far away. We did some flybys, so we went far away and come back quick. We were going away because around here, the perihelion would be reached. So we knew this was the maximum of the activity. When we came to this distance in June, Philae woke up because the illumination conditions improved on the comet. So we were far away at this time, so the signal was very weak. We tried to get closer, but we couldn't get closer than 150 kilometers without endangering the main mission and the spacecraft. So eventually we abandoned Philae in July. It had stopped talking to us anyway. And then we went away. We reached about 450 kilometers. Here we did an excursion in the tail for scientific reasons. Here we did another one. But after perihelion, we started getting closer and closer again. And eventually, the mission was extended. The mission was supposed to finish here, but it was so successful that, of course, we got the permission to extend it until the moment where Comet and Rosetta would go so far from the sun that we couldn't work with it anymore. So we knew that around September, October 2016, we had to finish the mission. So towards the end, we started daring a lot. And we did these flyovers at distances down to 2 kilometers from the surface. Navigation here became another incredible nightmare because the accuracy of these orbits became less and less. But we did 15 of these, and the scientists were super happy. And eventually, we decided to, instead of just switching off the spacecraft and saying goodbye, we decided to land the mother spacecraft on the comet. Of course, it was not designed to land on the comet, so we knew it was a suicide landing. But at least we did measurements down to the very last meter. And the last 2 kilometers we had never measured. Philae was on the surface. We had flown down to 2 kilometers. So the last few hours were extremely interesting for the scientists. And that was the end of Rosetta and end of 20 years of adventure for me. But let me show you another example, and then I should stop talking. Yeah, I have a few more pictures, but I don't want to go on too long. ExoMars TGO, our next mission to Mars, a big orbiter to measure the trace gases on the spacecraft, on the planet, and a test landing. This time, because we want to go to Mars next year with a proper lander, with a rover, we decided this time to do a test landing to learn how to land on the planet. So it only carried a couple of very simple instruments. The whole purpose of this was to show that we can land on Mars and to learn from it. This is the orbiter, this is the lander, Schiaparelli. This is the typical Oman transfer, yeah, of the mission, launched in March and arriving at Mars in October. And this was the landing site, very close to Opportunity, not that close as it looks here, yeah, but it was close. Landing on Mars, the first part is basically standard. You first use the atmosphere to lose about 90% of the energy through drag with a heat shield. Then you open a supersonic parachute and you slow down again. And then you're left alone your last phase. The last phase, the Americans have tried many ways. This is landing with retro rockets, landing with airbags, landing with this fantastic method, which is the sky crane. So this thing has retro rockets, but it delivers, while it's hovering over the surface, delivers the rover to the surface. Then you cut the cable and it flies away. We decided to do the last phase basically with retro rockets until the spacecraft, or the lander, would reach 1 meter from the surface and then drop with a crushable structure below. Because we wanted to learn from this landing, this time we didn't repeat the mistake with Beagle 2, and we had all sorts of observations. We had, of course, the orbiter, TGO, that would follow the telemetry during the descent. We had Mars Express that would follow the signal, at least during the descent, and then all these spacecraft that would collect data after the landing. But also we had a radio telescope in India that would collect the signal, just the signal, it couldn't decode telemetry, during the descent. So 3 redundant ways to follow the descent, plus spacecraft that would look at it afterwards. And we had a lot of telemetry, of course, a lot of sensors on the spacecraft itself to learn how it would behave in the atmosphere of Mars. And these are the tracks that our radio telescope was showing. You can learn a lot of things from this because basically this is Doppler shift of the frequency. But as you see here, at a certain point, about 50 seconds before the planned landing, could follow all the successful steps here, the signal stopped coming. We're not too scared at that time. We thought, well, maybe the radio telescope has a problem. But when Mars Express downloaded its own data as well, we saw exactly the same pattern. And so this was very bad news. What happened? Basically, everything went well in all this phase with the heat shield and the parachute itself. But in the very moment where the parachute opened, the inertial measurement unit on board the spacecraft, the lander, saturated for only 0.9 seconds. And the onboard computer ignored the flag. There's a number of errors here in the preparation, but the bottom line is that the onboard computer did not recognize that the IMU was saturated, so used these data as if they were true for 0.9 seconds. So its estimation of the altitude started deviating because the IMU was giving the wrong orientation. 40 seconds later, but this was just due to a timer, the front shield was correctly jettisoned. The altimeter, we had an altimeter, started working and it showed good data, but we didn't trust the altimeter. The computer trusted the IMU data and its own estimation, which is normally very robust. So it ignored the data of the altimeter and it said, oh, I'm actually too low. So it ejected the back shell 30 seconds later at 4 kilometers altitude. It should have happened at an altitude of 1.2 kilometers. And it switched on the engines, which worked very well. But 3 seconds later, it stopped them because it thought it had arrived. So instead of falling the last couple of meters, we actually fell for 3.7 kilometers. So eventually Schiaparelli fell for half a minute. and crashed. Nevertheless, this is very sad pictures taken by MRO, where you see the crater, you see the various parts, the parachute, the heat shield, and so on. But I consider it certainly a failed landing. I cannot deny, but it was a very successful test. We collected all the data we wanted, and we learned from the sequence of incredible, stupid mistakes that were made. And we think we're now much more robust for a next attempt. And ExoMars did also a new thing for us, which was aerobraking, which is losing energy around the planet, reducing the 24 hours very elliptical orbit down to a circular 400 kilometers orbit of 2 hours, using the atmosphere of Mars. Basically, this was the plan, the red one. This is the blue one, is the change of orbital period during about 1 year. It took 1 year. This is the period of conjunction where we were not doing anything. And you see here, for every passage in the atmosphere, we had a delta V, so a deceleration of about 1 meter per second. This is what we targeted on. You couldn't go too high, otherwise the drag would have caused a higher thermal flux. It would have damaged the spacecraft. You couldn't go too low, because otherwise it would have taken ages to lose all the energy that you wanted to lose. So this was a very, very tough exercise. In the beginning, with 24 hours orbit, this was relatively relaxed. At the end, with an orbit that was approaching 2 hours, I tell you, it was tough. But we learned this technique as well, which the Americans were using in the past as well. Very briefly, I've spoken about scientific and interplanetary missions, but ESOC deals with Earth observation missions as well. They are fantastic missions. They are very useful missions. They're closer to our life and to the citizens. Only from an operations point of view, they are boring. And that's why I don't talk too much about them. But they are so important, probably for our everyday life, much more important than going and orbiting a comet. Operationally, they are simple. They are just satellites that go around like this, altitude of a few hundreds of kilometers. They point the Earth, they collect the data. So the challenge here is not really operational pioneering. It's more reliability of the service, because you really provide the service to the citizens. And if you interrupt the service, then you have to talk to your customers, in particular the Sentinel satellites, like this one, which is Sentinel 5P. You talk to the European Union, and they're not happy if you interrupt the service, even for a few minutes. The real operational challenge beyond keeping the service is dealing with the space debris. You see here an estimation, 8,000 debris around the Earth, more than 1 meter, 40,000 more than 10 centimeters, 1.2 million more than 1 centimeter, hundreds of millions over 1 millimeter. These are estimations. And even small particles, of course, we can deal with the biggest one, the one above 5 to 10 centimeters. They are cataloged by the military, especially by NASA, sorry, by NORAD, by the Air Force, the American Air Force. So we can do maneuvers to avoid them, because we know where they are. And we do that. Every month we have 10 satellites in flight around the Earth nowadays, and we do 1 to 3 maneuvers per month. And we have 10 to 30 alarms that then the majority end up in no maneuver per month. But for the smaller particles, there's nothing we can do. And sometimes the smaller particles do hit you. This is a dramatic example. In 2016, in August, we got hit by a 2 millimeters, I think, 2 millimeters particle, one of our satellites, Sentinel-1A, and it did a crater of about 40 centimeters on the solar array. We were lucky that it hit the solar array. We lost only 5% of the power. Had it hit 2 milliseconds later, it would have hit the main body and probably would have destroyed the spacecraft. There's nothing you can do about these things, because you don't see them, and they can hit you. Now, the main control room was upgraded in ESOC in 2011. Now it looks like closer to a spaceship, so it's nice. The table, remember the table that I showed you in 1975? Look at it. And I'm very proud that I've seen and worked also on many of these. More than 25 of these launches I've been involved in different roles. Yeah. In fact, nowadays, this picture I took it myself in 2017. or we've started using this table as well. We've already launched another 4 or 5 satellites since. We have a very nice network of stations around the world, a 50-meter network mainly for low Earth orbiters. We have what we call the interplanetary network, the deep space network, 35-meter. We have a launcher tracking network of smaller antenna, and we provide services not only to the ESA missions, but also to third parties around the world. And we cooperate with agencies around the world. One of our most recent missions is Bepi Colombo, launched in October 2018. It's a train of 2 spacecraft, which is the European one, a Japanese one, plus a transfer module, which works with electrical propulsion. And okay, this is the sun shield for the Japanese spacecraft to protect it during the travel. We are using actively, not anymore as a test, operationally, solar electric propulsion. It works very well. We have 4 engines on board Bepi Colombo, and we use them, of course, for redundancy. We need either 1 or 2, depending on the phase of the mission. And the spacecraft is doing really very well. Also, to reassure you, we are returning some of the energy we've stolen with Rosetta to the Earth with Bepi Colombo, because you can use the flyby just by simple different geometry to slow down. So in fact, instead of gaining energy from the Earth and stealing it, you actually give it back. This is what we've done in April 2020. You see the orbit gets closer to the sun. In October last year, we did a flyby of Venus for the same reason. And we will do another one in August next year. You see it here. And then we will be close enough to encounter Mercury. And before we get there, because of course we encounter Mercury, but we still have too much energy. We have to get rid of it. And we will have to encounter it 6 times. Only at the after the 6th flyby, you see the orbit gets closer and closer, the energy gets lower and lower, and eventually we will have the relative velocity to be able to inject the spacecraft in orbit around Mercury. This will be in December 2025. Here, just some pictures taken by the optical cameras on board the spacecraft of the Earth flyby. I like the Earth rotating like a ball. This is really incredible. And okay, this is the geometry. We had to deal with an eclipse, so the spacecraft had to survive about half an hour eclipse. It worked pretty well. We did, as I said, in October, a Venus flyby, less dramatic. You don't see Venus rotating, but still pretty impressive. And yeah, the spacecraft is now en route for the next flyby. We launched, and this was the last project I worked on, and the last launch I did under my responsibility as head of operation in February last year, Solar Orbiter. A fantastic mission with this beautiful heat shield, which has to protect the instruments and the spacecraft from the heat of the sun, because we get very, very close to the sun, closer than the orbit of Mercury. This was the launch using an American launcher. It's a cooperation mission with NASA. We have also American instruments on board, but we do the operations. And you see again here, flyby strategy. The issue here is first to get into an orbit that goes between the orbit of the Earth and the orbit of Mercury, and then to change the inclination of the orbit so that not only we get closer to the sun, but also we see higher sun latitudes. And for this, we will periodically use during the mission the planet Venus. You see in this drawing, we're still relatively low inclination, but you see the inclination growing. And we will do several Venus flybys during the mission. And we will get up to, I think, 32 degrees inclination, or 35 degrees inclination. And closer to about 42 million kilometers to the sun. Let me mention, to finish, just a few things of the future. There is a lot of traffic in Mars. These are all the spacecraft which are currently at Mars. 2 are European. There are Indian, American spacecraft. There are Chinese and spacecraft from the Arabic Emirates flying today towards Mars. They will arrive this year. The Chinese want to land as well and to have a rover. They do all in one mission. very brave, but they are very good. They've just done it exactly the same with the moon. So they will have an orbiter, they will have a lander, and they will have a rover in one mission, in one go, first try. The Americans are landing also this year, and then we will have the Mars sample return mission, which is worth a presentation by itself. I don't have any more time for that. Let me mention another fantastic mission of the future, JUICE. May 22 is the launch, very, very soon. And look at the mission, 7 years cruise. We arrived there in the 30s, the beginning of the 30s. Swing-bys of Earth, Venus, Mars, delta V of 2.4 meters per second we carry with us, 6 billion kilometers journey. And then when we get there, we do a tour of the icy moons of Jupiter. We do a flyby twice of Europa, 13 times Ganymede, 14 times Callisto. And then we finish by 9 months around Ganymede. We will be the first ones to orbit Ganymede. This is the Rosetta of the 30s. And I hope that many of you, or at least some of you in the audience, will have the opportunity to work on fantastic missions like this. Another just conceived Comet Interceptor. We will use the launch of Ariel, which is an astronomy mission to L2, to launch also a spacecraft, which is called today Comet Interceptor. It will wait at L2 until a very exciting new comet comes, either a long period comet or even an interstellar comet. And then when it comes, we reckon it will come within a year or two, then we fly and we go to fly by this comet. The next comet mission, not exciting as a rendezvous, but exciting because we see something that is really coming maybe from outside the solar system. Finally, ESA, a bit better late than never, is going into the exoplanet science. We've launched Cheops 2 years ago, well, a bit more than 1 year ago, already giving successful, fantastic results. And we will go on with Plato and Ariel in the 20s. Earth observation will continue with some explorers, but also some fantastic Copernicus sentinels monitoring CO2, again, ice, land surface temperature, really beautiful, beautiful missions. All in this decade, by the way. These are all approved and the work has already started for those. And an exciting test also joined with NASA. NASA will shoot a spacecraft called Dott towards a very tiny asteroid. I think it's actually the moon. It's orbiting another asteroid. This is already small enough. I don't remember how big it is, but this one is less than 100 meters big. Didymoon is called, Didymos and Didymoon. And they will try to hit it, and then we will go with Hera, our mission, a bit later, launch in 2024, in 2 CubeSats. We will observe and characterize the system and try to see what effect the hit of Dart had on its dynamics. We do cooperation with the moon program of other nations, with China, with Russia, with Japan, with the asteroids, with America, with the Mars, and also with private missions to the moon. We support this Japanese-European joint venture to the moon with our antenna. So we have an exciting future also on the moon, although up to now we have not done very much there. I show this picture here to show that we deal with services, with knowledge, with technology, but we look not only at the Earth, we look at the solar system and even beyond, the galaxies, the gravitational waves, which I've not mentioned. There's so much on the plate and so much things for young people like you. It's an exciting program, and I'm so glad that I've been part of it, and that I've seen many young people grow, pick up the experience. They are now there flying these incredible missions to the unknown. And this is just an example of these people. This is a small part of my Rosetta team. I'm so proud of them. I've hired them. They've grown with me. And now they are there. They are leading the missions. They are leading the Earth Observation Division, the Planetary Division, the Bepi Colombo mission, the Solar Orbiter mission. These are all Eureka Rosetta veterans, and I'm very proud of that. And that's it. I leave you with a selfie from Rosetta, the back of the solar array, and the comet. And I hope it was not too long, but that's it. Thank you very much.
Thank you very much for this very interesting talk. I think everyone thoroughly enjoyed it. We've got one question from the audience who is wondering about what happened to the Ariane 5 launch during the cluster launch.
Yes, okay, I sort of invited this question, didn't I? Okay, so again, a chain of problems, but this is really an example of how when you have a catastrophe, it's not one mistake, it's an incredible coincidence, a chain of maybe 4 or 5 or 6. And normally the way you can avoid having these problems is testing. And so basically, let me try to recollect. When Ariane 5 was developed, it reused some of the Ariane 4 software. So Ariane 4 software was very, very reliable. There was a fantastic rocket. And the idea was we reuse the software and you better don't touch it, because software that works, you don't touch it. It's like a winning team. Yeah. There was a routine that was used only for Ariane 4. This routine was totally unnecessary for Ariane 5 because of the different, I don't know the details, yeah, but certainly this routine was running in the background for the first 40 or 45 seconds of flight. Well, the decision was, don't take it away. If we remove it, we have to change here, we have to change there. We take too many risks. Leave it there. It runs in the background. Who cares? Yeah, nobody uses it. Now, this routine used the estimated velocity, and Ariane 5 was faster than Ariane 4. So one of the variables in this routine went in overflow. And by going in overflow, it caused a chain of reactions, and other variables went in overflow. And basically, the two nozzles of the boosters suddenly went to their end position. Instead of being steered properly, it just moved to the end position. So the launcher suddenly went with an angle of attack of whatever, 40, 50, 60 degrees until the dynamic pressure destroyed it. So this is a chain of issues. Of course, there were problems in the software should have recognized the overflow. Of course, there shouldn't have been this link to other variables. Of course, somebody should have tested it in proper conditions. Of course, it would have been better not to run that thing. Imagine it failed 37 seconds after launch. Only another 5 or 6 seconds, I don't remember now, we would have made it. Yeah? But okay, this is the story.
Thank you so much. And thank you also for the incredible presentation showing all the highlights and also all the things to be hopeful for in the future. One of the questions that we also had from the audience, but I also asked myself as well, is much of the magic of space missions comes from these rigorous mission planning, everything from careful design to a wide range of testing and simulations, as you mentioned. And of course, this flexibility in being able to handle anything that comes your way. So one of the questions that we have from the audience, from Shirin Datta, asks, what are your thoughts on the newer concepts that ESOC may use, such as model-based systems engineering, to enhance that ground/mission operation?
MBSE is very fashionable these days, yeah? And who am I to say that is not useful? Of course it's useful, yeah? But let me tell you one thing. I like tools to support you in doing your work. The biggest mistake you can make, and I can quote, I mean, in my career, I can quote my mistakes and other people's mistakes in this sense. I can spend another presentation on this. The biggest mistake you can make is to say, okay, the tool is doing my work. So if I think that some of the people, especially those who are least experienced, they think the system engineering can be done by the tool. And this is the biggest mistake you can make. You need to be in charge as a human being of system engineering, and the MBSE tools have to support you. Also the methods, the approach. You have to always see it in support of your work, but not replacing your work. Sorry, it's a bit generic, but believe me, I've seen many young people say, maybe not voluntarily, but they have inside this thought, oh, great, I'm not going to use this tool and it's not going to do the job for me. It's extremely dangerous. Just to make an example of the past, when we started using spreadsheets, we did exactly this mistake. We used to do calculations manually or with a computer or with a command line, and suddenly you could put your numbers, hide the formula behind the numbers, and you will get the result. And we would not pay enough attention in just looking at the plausibility of the results. And I think in the meantime, we have evolved, you have evolved, you don't even think about this. You use spreadsheets, but you use it in the proper way. But in the beginning, we abdicated to the spreadsheets. And this was the biggest mistake.
Thank you for your answer. I'm sure Shireen Data will really appreciate it. We've got another audience member who says, thank you, Paolo. Would you be able to say something about the development of trajectory planning tools until now? How do you design superbly complex maneuvers?
So development of the trajectory planning tools and, sorry, the second part is?
How do you design superbly complex maneuvers?
Okay. You know, I haven't worked in that field. I've been sort of supervising these fantastic people that to me look like magicians. So I cannot go too much in detail in this. One thing maybe I can say, first of all, I think the question refers more, because normally that's very impressive actually, to this incredible sort of billiard game with the planets. And it's a combination. So there are relatively basic tools which simply have implemented at very high level. I don't know, Newton's law, not more than that. These tools have implemented this, and you put down your problem and your constraints. I don't want to have more than this distance from the sun, more than this distance to the Earth. I don't want to go too close to the sun, and so on. I want to have a certain inclination, my attitude, not more than this, not more than. So you put all those constraints, and you run the machinery. But by itself, the machinery doesn't work. It's like an optimization problem where you have to guide it. So you have to, you cannot just assume that it comes up with the right solution. And the guidance is a handful of basic, say, building blocks. For example, when we lost the first comet with Rosetta because Ariane had a problem, we had to delay the launch. We were left, and we had to find, within a few months, we had to find a new trajectory for a new comet, but that would fit with the existing spacecraft. It was built, so we couldn't go too far, we couldn't go too close. We had to find something that was very close. We found one, but our rocket was not powerful enough to get us on this trajectory. So you have your toolbox, and one tool out of the box is, if your rocket is not powerful enough, you just launch, and you launch on an Earth trajectory, Earth-like trajectory that brings you back 1 year later to the Earth, and you use the Earth as a flyby, basically as a delta V of your rocket. So eventually, after the flyby is as if you had launched 1 year before with a more powerful rocket. Yeah. So that's one of the tools. Or, for example, the flybys of Venus are another tool that you pull out of the box, and you say, okay, I want to go to Jupiter, and I need a certain arrival speed and so on. Okay, the only way is to get closer to the sun and get a big push. So I go to Venus. So these guys tell the tool first what to do. Say, okay, you know what? Don't start going around the solar system and finding, no, go to Venus, and you'll find out that the solution you probably find a solution. And then they go by several attempts. This is the way they proceed. Now, this is mission analysis. The real magic comes out once you have the trajectory, is actually to implement it. And there, a couple of Newton laws is not enough. There you have to look at general relativity. You have to have incredibly accurate determination of time, of position. You have to develop models of the forces that act on your spacecraft. In the best cases, the radiation pressure, but yet all these disturbance forces. And this is what we call flight dynamics. And what these guys do with their tools is absolutely incredible. And for me, this is magic.
Wonderful. Thank you so much. We have another question from the audience, very active audience tonight, which is great. Earlier in the talk, you discussed a little bit about the transition from, in the early days, some of the, let's say, the hardware issues that might have come about, some of the growing pains of learning how to deal with that, from failing solar panels to incorrectly working latches and so on. But then you said that there might be a transition towards software dominant issues. Is there any possibility you could give some examples on this and how we can solve it? Classics Explains does talk about it. You know, it's very hard to write software without any mistakes. So how is the best approach to solve these?
Yeah. Okay. We have a very practical lesson learned on this. So you're absolutely right. You can test the software as long as you want. Eventually, and if you have a long mission, again, forgive me, I use again Rosetta, but there are many other missions. Sooner or later, a bug will hit you. Yeah. So my recommendation, and we are implementing it now, is to have on top of your flight software, which normally is very, say, rigid, very dangerous to change, you know, because the thing is flying, and modifying flying software is always like, you know, like an operation on the heart while the heart is beating. Yeah. So you prepare your solid flight software, you do a nice and solid testing phase, and you consider that one day anyway you will have bugs, but you add on top of the software a layer of application software that you can actually use not to correct the bugs, but to overcome them. We have inherited, this idea was actually implemented in Eureka. I told you that Eureka was a futuristic satellite. I didn't invent it, but I learned from it, and I transported it in terms of requirements to Rosetta. I had to fight with European industry for decades. I'm quoting the title. The name is now well known. People that fly European spacecraft, they call OBCP, onboard control procedures. It's a very simple application software, very simple logic, yeah, that you can, as an operator, code and modify very simply without acting on the lower layers of the software. So it's not very dangerous to modify that. And so I had to fight with industry to sell this concept, and against all sorts of arguments. Yeah? Nowadays, you talk to Astrium, to Airbus, as the old name was Astrium, and they go around conferences and they make advertisement of their OBCP tool. And I'm very glad about that, yeah, because again, I haven't invented it. I used to say I was the prophet, yeah. So, so somebody else had the word, and I was just spreading it. So the word got to them. I have flown many missions where a deep problem of the ground software, of the onboard software, and even hardware problems, we have corrected them not by correcting the bug. We have corrected them by implementing a workaround at high level. We started with Exosat. I mentioned in the beginning, Exosat was reprogrammable. Suddenly the electronics, the hardwired electronics, kept saying, oh, this gyroscope is failed, this gyroscope is failed, this gyroscope is failed. And the thing would go in safe mode and using fuel and wasting time. And we were desperate. I mean, our flight control team was desperate. I was not in the flight control team. And one of the scientists said, oh, you know what? We developed a program in the scientific computer that checks the gyros. You keep your logic disabled, so it doesn't give you these false alarms. When the program that checks the gyros detects that the gyro has a problem, it switches on that logic, and the logic reacts. Yeah? So just a stupid thing like this saved the mission. And I have examples from Exosat to Rosetta to Goce I have thousands of examples like this. So this would be my recommendation. Put your software in a layered way, and you can't help it. Bugs will be there, but the higher level layers can not solve, but work around them.
Thank you. Now onto a more generic question. Do you know who designs the different missions and who suggests all the different missions? And if all European countries have a say in what missions are carried out?
Sorry, second part I haven't understood.
Yeah, sorry. If all the countries, since it's the European Space Agency, do all the countries have a say in what missions are set out?
Okay, it's a complex process. I will try to summarize it quickly. Basically, ESA is supported in the proposal of the missions, and then, of course, in the selection of the missions. Let's talk about the scientific program, but for the other programs, it's more or less the same. There is a fundamental difference that I will explain. But the scientific program is occasionally, periodically, ESA announces, okay, I have the next $500 million or $1 billion for a large mission, medium, small, and so on, to spend. Yeah, make proposals. And anybody in the scientific community, I guess not even European, probably you need to have a hook in the European community, but anybody can propose a mission. Of course, it has to make sense, so it has to be feasible. Yeah. But maybe I'm talking about a proposal of a few pages. Yeah. Then there is a committee, which is actually not an ESA committee, is supported by many universities around, that goes through a selection process. Actually, there's a layer of committees. They go through a selection process, and this selection process is quite complex. I'm not going to explain it. Eventually, these committees have a representative from all nations that contribute to ESA, so the 22 nations. Each one is equal, so 1 vote per nation. And eventually, you come to the proposal and say, look, we want to study these 3 missions. And they study the 3. Then the studies go on, and eventually, out of the 3, you have semifinals and finals and so on, and you select the one. That's the process. I think, yeah, you asked whether all the countries have a saying. Yes, they do. And in the proposal, I guess your university can propose a mission, no problem. Yeah, again, it has to make sort of sense.
Thank you. Keeping on this topic of international decision making, one of the things that we're seeing is an enormous growth in the space sector, and primarily in the private space sector. And many are starting to use the terms, let's say, new space in contrast to the old space where the dominating players were the agencies and the governmental money. Where do you see the space industry going in the next couple of years or decades? And what role will agencies like ESA play in shaping this?
Okay, this is my private opinion, of course, yeah, because you really need a crystal ball, especially to answer the first question. I lived, since I was a kid, I lived the evolution of space adventure. I mean, space was born 2 years before me. So I can tell you, it goes in waves, yeah? Waves and catastrophes afterwards. So first of all, there was the big hype of the moon. I was a kid, I was told we would land a human being on Mars, a man on Mars. At that time, we would only talk about man, but today we say human being. We would land a human being on Mars in 1985. Yeah, they promised me. I was a kid. I will never forget that. Yeah, we're still waiting for that. Yeah? So there was a big hype at that time, and then suddenly everything lost. Yeah, no political interest, no money. And space had to restart, basically. Then there was the big hype of the shuttle. When the shuttle was developed, and again, there I lived it, I was still in the university, but I know very well the atmosphere there. Space for everybody, reusable launcher, it will be extremely cheap. Citizens in space. I mean, one citizen died in space on the Challenger in January '86. Was a teacher. Yeah, they were flying politicians, teachers. They wanted to fly doctors, you name it. Yeah, we thought that was the future was there. Space was for everybody. All the best engineers in the first half of the 80s, all the best students wanted to work in space because that was the future. Then Challenger, big disappointment, another catastrophe, restart from scratch. So it went a bit like this, yeah. And I think today we are living one of these big hypes with the commercial space, which is fantastic. Don't get me wrong. The miniaturization is making really low cost. And this is definitely, out of each of these catastrophes, of course, you have gained something. It's not that you go back to square one. So this one will anyway bring a lot to space. Whether the future is a continuation of this curve towards a full commercialization and industry and the marketplace transfer to space, there I'm not so sure. This again, you need a crystal ball, and you will need to wait maybe 5 or 10 years. But certainly it is one of these moments, one of these revolutionary moments of space. So the second question is what the role of space agencies. I think whether this bubble explodes and goes back almost to square one, or whether really space takes off and becomes a commercially viable world, the space agencies have a very important role. In fact, especially in the second case. In the first case, they would have the role to recollect the pieces of the exploded bubble and put them together again. In the second case, they have a regulatory role. Well, they have the role of making sure that space remains usable. I'm very concerned about the space debris. I'm very concerned about the pollution of the radio frequency. Today is totally free. There is no regulation about that. You can only count that the commercial enterprises have their own interest, not to destroy their own space. But you know what happens, yeah? We are destroying our surface of the Earth. Who cares about space? Yeah? So that's a role that the agencies should take over, a sort of regulatory role. And also, of course, maintain the role of those areas which will remain, say, at least for a long time, not commercially interesting. Exploration, science, and those are things that actually drive technology, drive innovation, and only national agencies and international agencies can do that. Governmental agencies with the taxpayers' money. No commercial company today would take the risk and build a Rosetta mission. So I think that's, again, it's a very private opinion, but that's what I think.
Thank you for your answer. Someone in the audience would like to ask one more software question. And it is, have you ever encountered any hacking attempts? And how do you think about system security at ESA?
Okay, this is a very painful subject, yeah? Because yes, I mean, ESA is continuously attacked. Fortunately, we have never had, to my recollection, we have never had a serious problem. We had one problem during the launch of LISA Pathfinder, where basically, because of a hacker attack, we couldn't use one of our antennae. In fact, it was not our antenna, it was provided by the Italian Space Agency, but we could not connect because our computers were, you know, I'm not familiar with, there is a term when you actually keep pestering one computer, yeah, with millions of requests, and basically the computer cannot work anymore. So this was one of those cases. Apart from that case, I don't recall any serious case, but we have an army of guys that deal with IT security, and they tell me that they are pretty busy to defend. Yeah? I said it's a painful subject because as an operator, you need to fly these things, and the security guys, their ideal world is that you do nothing. So if you don't do nothing, if you do nothing, then there's no danger. Yeah? So we are in continuous, not conflict, but let's say drag, because we have to do things, and for them, ideally, we should not do them. So they have to help us in doing them safely, and we hate whatever they tell us. But of course, it's an important subject. Yeah? Whenever you introduce security, you have a trouble for the operations people. Yeah? So they will hate you, but we cannot ignore it. It's clear.
Thank you, and it is a very, very important topic. Going back to one of the things that you were mentioning before about space debris, which is increasingly of concern, not just because of the number of objects increasing dramatically, also because of the space boom, but also because the number of conjunction events where objects are passing close to one another are enormously increasing every year. One of the solutions that ESA has in its plans is this so-called object remediation, this capturing of a defunct object that may be tumbling as well. And we know of one company, Clear Space, that has been awarded a contract. I just wanted to know, as an operator, what your thoughts are on the challenges, the unique challenges that may be coming from that kind of a mission.
It's an extremely challenging mission. I have to say, this is the type of, again, very private opinion, in heavy conflict with some of my management. So take it as a very private opinion. It's not the opinion of ESA. This is the type of mission where a space agency should pioneer, not as a commercial enterprise. ESA decided to go in the direction of a commercial enterprise, and I simply disagree with that. I don't think it was the right decision. Having said that, so because this is a mission which involves new technology, it involves new operations concepts, it involves even legal aspects, yeah. And I don't think it should start. I'm not saying that it should end. It should end commercial. Eventually, you should have a sort of garbage collector company, yeah, that you pay, the governments pay, and the garbage collector company collects the garbage. Yeah, the governments don't do that themselves. But initially, the system should be developed, proven, and and made operational under a very tight supervision of a national or international agency, a governmental agency. ESA started with this idea. Oh, no, we leave it to them. They'll sort it out. My opinion is that we will have to increase our supervision into that. But maybe not. Maybe I'm wrong. And maybe they will do a fantastic job and it will start from scratch. But I see ESA as being the one that in the past we pioneered with the telecommunication satellites. No, nobody would come to ESA to build a telecommunication satellite. We pioneered with meteorological satellites. Now we still build, well, we sort of do the project management, but it's done by industry, you know? And even operations are done by separate agency. Galileo, all sorts of things. We pioneer in a field, we reduce the risks, and when the risks are below a certain level, then industry can go on their own. This is the way I see that.
Thank you. Someone else in the audience asks, well, thanks you, first of all, for your talk. And then they ask, you have mentioned a few times that you have been able to work with some incredible engineers. What characteristics do you think make the best engineers?
Yeah, well, let me start from saying engineers is already reductive. Yeah, I'm a physicist, for example. But jokes apart, one of the, in my opinion, the success factors of the operations teams that I've been working on and then eventually leading was the diversity. And diversity, okay, already we are very lucky in the European Space Agency. By definition, we work with nationality diversity. This is an incredible enrichment, believe me, because a British engineer is different from an Italian engineer, from a German engineer. So you take guys that in principle are qualified exactly the same, but they have different qualities, different strengths. And if you combine them properly, it's the sum is much higher than a single nation engineering team. So diversity in nationality, but also, and for me it's very important, it was typical of operations teams, by the way, where you do not have the operations engineer by academic education. Yeah, we got, of course, aerospace engineers, but we got physicists, mathematicians, informatic engineers, telecommunication engineers, and this. If you mix up these people in the right way, you get the best. I would never, I'm a scientist as a background, and I would never fly a mission with a team of scientists, for God's sake. But I think that also a team of engineers, without an injection of some of the different frame of mind, different type of creativity from a scientist, can obtain the best. So diversity is the key. And we were diverse. Of course, diversity of gender, diversity of age. Yeah, I'm not talking about only background, nationality, background, age, and gender. When I started, I made already a hint to that. When I started, control rooms and operation teams was a male world. Yeah, women in there, like on a submarine. Yeah, took ages before getting a woman on a submarine. Well, we felt exactly the same. Yeah, and the incredible enrichment we gained when we started getting female components in the team was actually visible. Nowadays, nobody would think of a single gender team. And so diversity was the key of the success, one of the most important elements of the success.
Fantastic, thank you, and that's a great note. Just in the interest of time, I think this might be the last question that we have. I noticed at the back behind you, there's a Saturn V rocket, which I can imagine is a source of inspiration. And so I just wanted to ask, as a closing note, what source of inspiration do you see for a younger generation, a new generation of scientists, engineers, and all sorts who might be keen to go into the space domain?
Oh, that's a very interesting and difficult question. Let me start, while I think of a proper answer, let me start with something that I felt very strongly. With Rosetta, for the first time, we felt that there was a very worldwide audience, lots of people, and in particular, lots of kids. So we got so much feedback from the kids. And I want to believe, and I really hope, that missions like Rosetta have inspired and will inspire little kids, like the moon landing inspired kids like me. I was 9 years old when they landed on the moon, and this has formed my life. Yeah, and I want to work in space. I want to be an astronaut, and then I want to be a scientist, and everything comes from that. This is a Lego, by the way, Lego model that my kids gave me when I became 16. So it's extremely important to have inspirational models. Yeah, and I really hope that missions like Rosetta are. I'm not sure whether I'm answering your question, but one thing that has been the experience of my life, not only with the moon landing, but many times also in the career, is that if you have something that makes you dream, and you keep it also always in the back of your mind, whatever choice you do in your life, even if it looks like it's going now 90 degrees away or 180 degrees away, eventually you will always pursue and find a way to get back into the track of that dream. So whether the inspiration is a mission, is a person, yeah. Sometimes you have a teacher in university that inspires you. We had a mathematics teacher in the high school who was simply charismatic, yeah. And this lady was so charismatic that eventually 1/3 of the class decided to study either physics or mathematics. Yeah? This is crazy, yeah. But you need to choose your model, choose your inspiration, either person or mission or field, and follow it. Eventually you get there.
Thank you, that's very inspiring. I think that's all the time we had for today, unfortunately. So thank you everyone for coming, and especially thank you to Dr. Paolo Ferri for giving this amazing talk.
Thank you for inviting me. It was really a pleasure, and thanks for the questions. And call me again. as you see, I like talking. So
Thank you.
thanks. Bye-bye.